with that. Okay, so hi everybody. This week we're very happy to have David Curtin from Toronto talking to us about no-lose theorems for discovering new physics in muons. So David.
Okay, thank you very much for the nice invitation. By the way, because this is sort of a slightly different way of giving the talk, it kind of makes it a bit more fun, I think, because I can dance in front of the slides. But if it's ever giving trouble with readability, just let me know and I'll just switch to normal screen sharing. So, okay. And as usual, just unmute your mic and shout at me in the middle of the seminar. That's totally fine. Okay, so I want to tell you about physics that's connected to g-2 and the very ambitious statement of a no-lose theorem. And I want to very strongly highlight the awesome people that did this work, especially my postdoc, Rodolfo, and of course also Yoni and Gordon, who you guys know. So this needs essentially no introduction at a time like this. Okay, we've had a couple of weeks, I guess it's been 4 weeks ago by now, the g-2 announcement. And the sort of moral upshot that I want to convey is that, now, unsurprisingly, if this anomaly is real, then there is BSM physics and it talks to the muon, right? Like we learned two things. And that sort of means that a muon physics program from GeV to 10 TeV or so will find new physics. Now, I want to make clear that I'm not saying that the muon collider is necessarily the only way to find these things. But the argument is very clean and easy. So bear with me and let's charge ahead. So I'm going to very, very briefly overview g-2. And this is really just couching the various possible controversies that regard the BSM status of this anomaly so that we can go into this with a sort of honest mind. But if we choose to be optimistic, we can think about BSM physics. And of course, that's a very well-trodden subject. So I'm going to sort of go through this in only the coarsest outline before zooming out of any one particular model and talking about a model-exhaustive approach, where we really just try and think of all the possibilities in some, at least in some way. And this investigation, which is the subject of our two papers, yields some very, very concrete experimental targets for discovering BSM physics. And I mean, that's just a sort of universal statement. And from that experimental target, we can formulate various experimental programs. In this case, like I said, I'm focusing on low energy experiments and muon colliders. And then I'll leave you with my conclusions, which is the sort of summation of this no-lose theorem. And as usual, like I said, interrupt at any time, we can discuss live. Okay, so very briefly on g-2. So everyone here by now knows that we're essentially talking about the chirality flipping photon interaction of the muon, which is induced at loop order. You can calculate it as a QFT homework at one loop, and then by now, of course, the current theoretical state of the art has all these contributions. It's some high ordering QED and various other contributions, Electroweak, QCD, and so on. And the latest state of the art is from the g-2 theory initiative white paper. And this number for the anomalous magnetic moment of the muon has to be compared to the actual measurement. And like I said, E821 at BNL or g-2 at Fermilab both got essentially within statistical uncertainties the same results. So if you combine those, you get an anomaly, a deviation from the standard model of about 2 parts in a billion at a sort of 4 sigma significance, whatever that means. Now, where does that leave us? So the future of the experiment is very bright and very exciting now that everything's online and taking data. Fermilab will have reduced the uncertainty by a factor of 2 by next summer, and eventually it'll reduce the uncertainty by a factor of 4, the experimental uncertainty. So this is enough to mean that the deviation significance becomes completely theory dominated. And it's also very, very good, pardon me, that from what I understand, there's sort of no real worry that, of course, Fermilab g-2 uses some of the big hardware from the BNL experiment, but a lot of things have changed. And I haven't really, again, speaking as a sort of, gossip monger, I haven't really heard anyone worry too much about anything in particular being wrong with the experiment or systematic. But even so, for anything that's important, you want to confirm. And J Park has planned to supply us with a similar precision measurement using a completely different setup and methods within the sort of 5 years time span. So that'll give us independent confirmation. So on the experimental side, things are pretty good. On the theory side, the only thing I really want to talk about is the hadronic vacuum polarization. That's the stuff that matters. And again, this is something that's been flying in the airwaves, but let me kind of give you my bird's eye view on it, which is, I'm not an expert on the details of this, but this is sort of my understanding. So the most controversial part of the standard model prediction is this hadronic vacuum polarization, where you have a photon in the vertex correction and it essentially talks to QCD. Now, you cannot calculate this from first principles perturbatively because it's strongly coupled physics. What you can do is use the optical theorem, and you can measure this in data. And this is what the G-2 theory initiative did. They they essentially used a combination of the Babar and Chloe measurements of essentially this hadronic vacuum polarization. And you can see that there's a little bit of a disagreement there. It looks like, I don't know, but the data was combined in such a way that if you were to, so it's my understanding that if you were to remove any one of these two, the significance of the anomaly would only go up. So they were sort of careful to take into account that the systematic uncertainty. But of course, okay, it would be great if these could agree better. But this was done quite conservatively, and my understanding is quite reasonably, and this is where the current thing comes from. But of course, BMW has been making waves with its lattice calculation, which does try to compute this from first principles, as do other lattice calculations. The difference, of course, is that BMW has record low uncertainties to the point where their statistical uncertainty within their lattice ensemble is insignificant compared to the systematic uncertainty. And those are really thorny for these calculations. So what do you do? What do you make of this? Do you say, screw it, it's not real BSM physics, the lattice clearly proves, no. I would say it's really, you have to really be very careful and reserve judgment one way or the other, because a single lattice calculation does not upend a consensus, and it's really crucial that other lattice calculations confirm this. That's point number one. But point number two, it's not as though if BMW is correct, everything clicks together with a big click and everything's perfect and everything's fine. If BMW were to be correct, then there is some increased tension with electric precision, greatly reduced tension with G-2, but there is sort of 2 point something to 3 sigma tension with sub-GeV hadron data. Because again, at the end of the day, whatever this is and whatever that's calculating, it should show up here. So there's something a little bit strange somewhere. But if you add up all these sigmas, it doesn't add up to 4 sigma. So it does demonstrate the non-Gaussianity of theory errors in this G-2 prediction. But even so, there's no clean story that makes anomalies go away completely. And we really just have to wait. So on the experimental side, it's my understanding that Bell 2, I think, will provide us with data pretty soon, and maybe on a slightly longer time scale, even cleaner mu1e at CERN. And new lattice calculations are on this. And probably within a year, we'll get a clearer situation. So,
hey, David,
yes.
Oh, sorry.
Yeah.
May I ask? So suppose you used just G-2 data. Forget about BMW, and then you go the other way and ask to predict the scattering data from it. Would you again say that the disagreement is only 2 sigma? Suppose you predict hadron polarization from the muon G-2 measurement.
So firstly, I mean, at the end of the day, the thing that enters the G-2 is a sort of integral, not like the shape of this curve. So I'm not sure if you can kind of go back 1 to 1. But that being said, I see. So you're asking, let's take G-2 as the measurement of the hadronic vacuum polarization. Well, sorry. I mean, the answer is this, right? So the lattice claims to be almost at the experimental level. Mm-hmm. And the point is, if I take the lattice as the input, then I get this. So the reason I put 2.xx is, anyway, but you get 2 point something to 3 sigma disagreement with hadronic vacuum polarization. So that's telling you if you take this as the input. If you take this as the input, then this tension would grow. So maybe it's at 3, maybe it's at 4. You know, maybe in that sense it is Gaussian. I don't know the answer, but it would be more than this. Yeah.
Okay.
If that makes sense.
Thank you.
Yeah.
David.
So this whole yes, absolutely.
Well, you're sorry,
hey,
you hadn't finished your answer. Hey, David.
No, I'm good. Hi, John. How's it going?
But I didn't want to.
Go ahead.
The other question. The other.
No, I think we're done. Go ahead.
Okay. Yes. So I one of the things that worries me is the difficulty of, in fact, the experiments that measure the R ratio, and the difficulty of that theory. So I spoke to some of the people who, not on the white paper collaboration, but I spoke to some of the experimentalists involved in extracting R, you know, in these data sets, and they're concerned. They are concerned about this disagreement between data sets, and they are concerned about, you know, there can be hidden things. After all, there are, you know, there are incredible sort of effective non-analyticities all over the place, right, in this measurement, that you have to model extremely well, and there is some systematic difference also just in the shape at various stages as well.
Yeah, no, absolutely, which is why the BEL2 data is going to be really, really interesting.
Yes, I agree. I mean, it's a very important thing to push on, which is this other data thing, rather than, I mean, JPark, I'm, you know, sympathetic to, and it'd be nice to have a totally independent measurement, but I think there are other things as well, right, we need to do.
Oh, I mean, like I said, my money's on JPark agreeing with BNL and G-2, right? Like that's kind of my, like I tried to ask experimentalists if, oh man, it's the same ring as BNL. Is it possible it has the same bents or something, and that's why you get the same thing, you know?
Yeah, I've heard that. That's incredibly unlikely. Yeah, no.
So that just doesn't seem likely by the people that know about this stuff. And you know, yes, JPark should confirm. It's super important because, you know, if this really is BSM, then you need every confirmation, absolutely, right, in a sort of good citizen sense. But the thing that I worry most about is essentially this and this. I completely agree with you. But I mean, that'll get updated on like one. So the point here is there's 1 year timelines everywhere here, right? BEL2 I think has the data, and they need to release it. And then the other lattice groups are on this, you know, with enthusiasm. So within 1 year, I think the situation is going to get a little clearer.
Yes, before you move on to other things and muon g-2, you know, and the no-lose theorem, are you know, there's also an anomaly in g-2 of the electron that goes the other way, as you know. There's about 2.6 sigma
it's a
or
little
something
smaller.
like this.
Yeah. No, it's gone. It's gone.
Yeah, it's gone.
Oh, it has gone?
Hasn't it gone?
There's a new measurement of alpha which shifted by a few sigma, and it's on the other. It's on the other side, but it's almost nothing now.
Oh, okay. Well, thanks, Lance. That's
the Muller measurement. There's a new one by a French group.
Okay,
it's like 3 sigma away from the Muller measurement. So.
Oh, okay.
Well,
thank
closer,
you.
but not exactly on top of, but on the other side of the g-2 prediction.
Thank you for telling me that. Okay.
So you can make models with the same sign now if you want.
Excellent. All right.
But it's weak. It's
yes. Okay. Good. No, I thought the Muller measurement was the absolute state of the art. But did Muller mention that in his talk at KATP or something?
Yeah, you had to wait till the end. He
I missed it somehow.
He said, and now for the future. Oh, actually, it's already the present.
Okay.
And then he mentioned the French measurement.
Okay. Thank you. Okay.
And he doesn't know, you know, what's going on between the two. He didn't say anything about that.
Okay, thank you.
Actually, I wanted to ask about the third lepton, the tau. In other words, you could try to do some of the same physics in tau decays, and it's murky because of, you know, isospin corrections when you rotate from the charge current to the neutral. But the tau data is always higher than the E plus E minus data. It may be that the corrections are not being.
I tried looking at this briefly, and you know, running the same thing, and it's just the precision for the tau, because you're really looking at decays. You can't like integrate over time and you know, make it macroscopically do things in a magnetic field and stuff. So the precision, if you look it up in PDG, it's like 3 or 4 decimal. You know, it's sort of it's total shite by the standards that's required for this kind of game. Even because think about it, the g-2.
David, Lance is talking about the determination of the hadronic vacuum polarization from tau.
I'm sorry, I thought you were talking about g-2 tau. Okay, I'm sorry.
Measurement of the tau magnetic moment.
Sorry, I'm sorry.
I meant that you can rotate the tau hadronic decays like it decays into rho plus. And so it should tell you something about E plus E minus to rho by an iso rotation. And so people have done this, sort of they do it the other way nowadays. They use the E plus E minus data to predict the tau branching ratios through, because you have the differential spectrum in E plus E minus, and you just have one integral for the tau.
Yeah.
But there are discrepancies when you try to do that comparison. And whether it's a problem with
Okay, good.
understanding isospin rotation at the required level, it's not clear. But all I'm saying is the tau data is sort of on the side that's towards the muon g-2 measurement. It's bigger.
So it's towards the g-2 measurement.
Yeah.
Oh, sorry. Yeah, okay. But again, yeah, but okay. But my impression from the chatter was that is not something that is not as firm as any of this stuff, like you said.
It's not totally firm, but nothing's totally firm in either. Yeah.
Well, I mean, but the point is, hopefully things will become significantly firmer, right? I mean, the two avenues by which they hopefully will become firm is more lattice calculations and the Bell-2 measurement. I think that's kind of.
It'd be great to hear from Bell-2. I don't know how fast that will be because it's very tricky to get these normalizations right.
No, I agree. I don't have a good prediction on that time. Yeah, but they sort of, like, I hear soon because they sort of have it, and then. But how do you release it? Yeah, I don't think it's limited by the data right now. It's just about how to analyze it. But okay, look, let me move on. So, but you know, we're putting on our optimistic hat. So the question that we want to address is, if the g-2 anomaly is real, what does it mean for BSM physics? Yeah. Now, this is a super familiar topic, so I don't want to go into any specifics. Because there's literally order 10 to the 3 to 10 to the 4 papers over the past decades that deal with BSM explanations for the g-2 muon anomaly. But essentially, it could be almost anything as long as it couples to muons, right? As long as you get some kind of a loop correction, and the crucial and the chirality flipping part of it, and the chirality flip could come just from the muon propagator, so it doesn't even have to live in here. Could give you this contribution, and it could be connected to dark matter, it could be connected to SUSY, it could be connected to axions, could be all kinds of other new physics motivations. So, you know, I don't really care about any of these models for the purpose of this talk, and just to demonstrate that, you know, we of course consider things as low as a GeV or above a TeV. So you have sort of very classical semi-visibly decaying dark photons. So the dark photon could explain it sort of in this band, and there's still a little bit left where it could be explaining it. Or you can have sort of Electroweak multiplets, some of which are dark matter in the multi-TeV range that could easily explain dark matter and g-2. So there's a whole range of such general new physics contributions that could. This is such a general new physics contribution that could be coming from almost any BSM theory. Yeah. So we kind of want to ask a simpler question. Which is, you know, whenever you have an embarrassment of riches when it comes to possible explanations, you care about, number one, how do I distinguish between them? But even before you think about that, how do I find any of them? That's really the only question that matters right now. How would I find any of them, regardless of the complete theory? Yeah. So in order to answer that question, we took what we call a model-exhaustive approach. And this might sound pedantic, but we settled on this particular terminology to distinguish it from the model-independent approach, which is just means the same thing in terms of words, but a model independent is what people talk about when they typically mean essentially EFT analyses, right? So if you want to do a general BSM analysis of g-2, the sort of intelligent thing to do is to parameterize unit physics as some non-renormalizable operators, and within the SU2 gauge invariant standard model that has a Higgs left and right hand lepton, and it's dimension 6. And this will give you g-2, and the measurement will tell you that if you put a 1 on top, if you put roughly 1 on top, then m is roughly 200 TeV. So okay, so that doesn't teach you a whole lot beyond that this operator is generated, and this mass scale seems so huge that you kind of want to scratch your head and go, could it really be that high? And what would that mean theoretically? But we would like to not just talk about the problem with, of course, an EFT approach is that it only is valid if you're probing physics at a scale lower than all the masses of the particles. And therefore, you cannot discuss direct signatures like discovering where the new particles are at, like seeing the new particles. So we want to talk about direct signatures. And in order to do this, we will assume perturbative unitarity. And then we can look inside of the 4-point function, because basically that just means that this 4-point function has to be drawable as a Feynman diagram. And we want to do this in some way of quote unquote full generality. Okay. So essentially we want to construct all the possible loops that you could draw here, and with caveats, but caveats that hopefully do not diminish the usefulness of the result. And that'll allow us to draw conclusions that are as general as the model independent analyses, but regarding direct signatures. Okay. So here's the recipe for our model exhaustive analysis. And these little stars, by the way, represent things that some of these little caveats, but they're all pretty defensible. I'm happy to talk about those more, let me say offline, or if anyone wants to interrupt me, but I'm going to kind of go over those. So I'm going to assume that new physics is based perturbative unitarity. So essentially it kind of means something that I can calculate perturbatively. I'm going to assume that the g-2 contribution arises at one loop. And at 0th order, that is just because a higher loop contribution is going to have more suppressions and be at a lower physics scale. And there's various ways in which I would see those indirect signatures even easier. We can discuss this more, but for now, let's just say one loop.
Actually,
then
David,
I'm going to,
David,
yes.
can I question you on exactly that? So
yeah, sure.
Nathaniel was worried about
Yes.
an exception, a possible exception, right? Which you probably remember.
So we're not too worried about that one. We're investigating it a bit more carefully, but essentially you're going to get deviations in Baba scattering that are similar to what we calculate, because it comes from almost the same operator that gives you g-2.
Yes, and I was worried just about whether this is observed. So I was hoping you'd actually update on exactly this. So, I mean, just to say,
no,
I mean, there was a worry.
Well, well, like I said, the Baba scattering is going to be the quote unquote the indirect muon only signatures are going to be there, and the mass scales of particles is going to be even lower. So we are right now actually investigating these singlet type solutions a little bit more. I don't have an update on that yet quantitatively.
Fair enough. No. I wanted to know. But yeah. So I mean, there is, in other words, there is a potential loophole. I think it hasn't been fully closed.
I actually don't think so, because, like I said, the indirect signature of Baba scattering will not be smaller for something like this, because whatever the multi-loop effect is, it still has to give you g-2. So
Okay,
so
John?
it'll
Yeah. Yes.
John, your claim is there's an interesting model that evades these assumptions. Could
No,
someone
it's actually
tell me what it is?
Nathaniel. Yes, Nathaniel actually was wondering about this. I mean, there's no proof. It's not like Nathaniel or myself have done a calculation and said, but the question is about whether you have a singlet with a Z2 symmetry. So you have an S squared interaction, and g-2 arising now at 2 loops, not 1 loop. And the problem is it seems to possibly mess up the low energy signatures you'd look for now because it's 2 loops.
I actually really don't think it does, though, because you'd still have this multi-loop interaction would still generate a muon photon interaction, and it would, therefore you can break that apart and get Baba scattering deviations. And I don't.
Well, maybe we should come back to it when you discuss the singlet models. Yeah. How about we come back to this when you discuss the singlet models, because then it will be clearer to.
I think that's probably a good idea.
Yeah.
Okay.
Sorry.
So so with these assumptions said, and I mean, by the way, all these little stars, like within our assumptions, you know, if you don't want to worry about it, just take these assumptions and then you know, run with them. But there's a longer conversation that we can have why we don't think these assumptions change the validity of the conclusion. But okay, so let's just stick with these for now. So we're going to look at all possible standard model gauge representations of the new particles in the loop. We're going to look at all possible Lorentz representations, which practically means spin half, 0, 1, 0, a half, and 1. The possibility of a gaugino was essentially discounted as being suppressed in g-2. We're going to assume an arbitrary multiplicity of new particles. So you know, if the new particles have color, then this would be at least 3, say. But if there's just a bunch of them, you just have some number. And all possible masses and couplings that generate your deviation. And then you ask, within this very general model exhaustive analysis, what are some irreducible experimental signatures? Okay. So the way to make this problem manageable is to cleave the space of solutions along the gauge representations. So you have singlet scenarios where the new physics in the g-2 loop is standard model singlets only. And this is an extremely simple theory space, right? You just add some kind of a singlet and it gives you a new loop. And the phenomenology is more complicated because singlets can do more strange things. They're not protected by symmetries or whatever, so they can do strange things. They can be invisible, they can decay in various ways. So the phenomenology is more complicated. Everything else we call an electroweak scenario because this is new particles with some non-trivial electroweak representations in the loop. Like if it's not this, it has to be that. And this is a complicated theory space, but the phenomenology is simple because you always have charged particles. And charged particles are, experimentally loud in some sense compared to these singlets that could be all sneaky. So this is the sort of cartoon of how we split this up. And this theory space of singlet scenarios and electroweak scenarios is mutually exclusive, but exhaustively covering the state of possibilities. And the kind of signatures we'll talk about for singlets is new physics in muon annihilation and scattering. For electroweak scenarios, new charged particles. And we will also talk about the indirect signatures that are a result of these kinds of models, which are in fact part of the model, quote unquote, independent analysis within an EFT framework that were done, I'd say most importantly by Dario and Paride. So this is sort of all part of the ingredients. So let me go through these one by one. So for singlet scenarios, the story is very, very simple. You can imagine adding a vector or a scalar. I don't discuss a neutral fermion because that would essentially give you a pure right-hand neutrino type solution where the g-2 is too small. There's an interesting pseudo-dark axion edge case, which also will be discoverable. So these don't change the discussion. So let's focus on sort of like a dark vector, like a B-L gauge boson or a dark photon or something, and a dark scalar. Now, there are, of course, existing experimental constraints on many of these, but let me just not worry about that for a second, because certainly for the scalar, there's a lot of unexplored parameter space, and one could imagine some here, okay? And really, all you're doing is you're adding one particle that couples to the muon. And you get a g-2 contribution that you can calculate very straightforwardly. And for sort of order hundreds to 1,000 GeV masses, you can, with order 1 couplings, you can get exactly the g-2 that you need. So that part's not super interesting, theoretically. Essentially, you have a coupling to the muon that goes proportional to the mass of the particle if you want to satisfy g-2. And for scalars, the one thing that we did do here is we very carefully calculated the unitarity bound on these couplings with the proper order 1 factors, and you essentially get a requirement that the singlet in this solution has a mass of less than 3 TeV, regardless of the multiplicity of the singlet, because everything sort of cancels, okay? So you have something that couples to the muon proportional to its mass below 3 TeV. Okay, good. So that's singlet scenarios. We're going to discuss the experimental signatures in a sec. So John, let's maybe circle back to that then, okay? Let's talk about electroweak scenarios. Now, those are more complicated. Yes.
David, I don't think anyone's
Michael.
quarreling with 3 TeV, but I'd just like to remind the audience that perturbative unitarity is really a qualitative criterion. Eventually, something unitarizes the model. There are examples
of course,
well above
of course.
The perturbative unitarity limit. So you have to assign some factor of 2, at least, error to any perturbative unitarity limit.
Sure. Of course. I mean, the truth is, the way that I would look at this is if you have a theory that gets even close, because, okay, so very, very literally, if I had a theory that was right at this bound, then I, by definition, don't trust the theory. Right? Exactly. So if I had a strongly coupled theory, like by definition, I would have a strongly coupled theory, and then there is some fuzziness, exactly like you said, because we don't know exactly what it does. But this is kind of what I mean when I say that we couple perturbative theories, and any theory that's perturbative would be way below that, right? By some healthy order 1 factor, say. And if it is anywhere near that, it really is a strongly coupled theory, and you don't know exactly if it's 2.5 or 4 or something like that. Yeah. But that's kind of what I mean, where because we take this unitarity bound as a sort of quantitative edge, that edge should parametrically track what even a strongly coupled theory would do.
Parametrically,
within that uncertain, you know,
we'll have to
parametrically.
look at the eventual statement of your no-lose theorem. It may not be as precise as you imply.
Fair enough. Fair enough. Okay, good. Very good. Okay, so let's move on to Electroweak scenarios. In general, this is a complicated model space because you need to consider all non-singlet one-loop possibilities. Yeah. But Electroweak scenarios can give you some
David,
different.
I'm sorry. So we missed the discussion that you promised before. I guess Nathaniel's point is that if you go to two loops in the scalar scenarios, then you can couple back to things that couple to the photon. And with a somewhat heavier mass, with a somewhat lighter mass, the scalar, you can generate a g-2.
I mean, I'm going to talk about the experimental signatures of the singlet in a bit, but yeah, I guess Nathaniel's point is if you have a Z2 symmetric singlet, which by the way, I mean, are we talking about a mu SS coupling? I mean, we were sort of starting to. I haven't thought about this in the last few weeks, but at any rate, sorry,
it's all new to me.
Yeah. So, yeah. So let's see. We talked about this a little while ago. I guess if you have, actually, John, do you remember the details of Nathaniel's model? Because I remember we talked about it weeks ago, and then I haven't dealt with it recently, so it escapes me right now. John? Okay. I mean the truth. So okay. So I guess the thought is if you had some Z2 symmetric kind of coupling where the g-2 diagram can only be generated at two loop, then you know the sort of precise reasoning of our argument is different. It doesn't apply in the exact same way. But we are going to actually derive, for example, the Barbour scattering correction that comes from the singlet in this case, because if you have new physics that talks to the muon and gives you a g-2 type diagram, then you're going to also get corrections to Barbour scattering, which is just mu goes to mu. Yeah, and it's very hard for me to think. And that Barbour scattering is a very important signature. That's, you know, in our case at a low energy muon collider is hard to miss. And it's very difficult for me to imagine that something that generates that same operator at two loop would not generate that Barbour scattering.
Yeah, so I shouldn't really speak for Nathaniel too much because I don't want to mess up. I mean, his thing. I mean, but I was thinking that Nathaniel was thinking that the kinematics that would actually be somewhat different.
Yeah,
I mean, he was worried about the.
It's really hard for me to think that's a problem because again, ultimately we're talking about, you know, like in order to exclude. So okay. This is preempting the experimental discussion on this. Yeah. How about we talk about this?
Yeah, no, sure, absolutely. I mean,
okay, all right. So Michael, let's hold that thought until I talk about the experimental side a bit more. I think at that point maybe it'll become a bit more clear. Okay, so back to Electroweak scenarios. So one thing that's kind of qualitatively different about these scenarios is that because you have new particles with electroweak charges, you know, the g-2 operator relies on having a Higgs-Vev insertion and a chirality flip because you have a mu left going to mu right, and that requires a Higgs-Vev and a chirality flip. Now, both of those things can be the muon mass, and that's the case for the standard model. Sorry, that's the case for the singlet contributions. But if you have new electroweak charge stuff in there, you could have, for example, a fermion have a chirality flip that comes via Higgs coupling. So now you can have a BSM coupling in here that can be much, much larger than the muon Yukawa. So now you can have a g-2 that only scales with a single power of the muon mass instead of two powers. The single power just comes from the fact that it's a muon observable and so on. So this means that the mass scale could be much higher because the numerator is larger, okay? And if you're talking about new charge states with high mass scales, then you sort of are drawn towards BSM chirality flips, okay? So you can get to much higher masses is the general point. But the experimental signatures are much, much, much simpler. New charged particles, okay? Now, why do we focus on new charged particles? They're sort of the easiest to discover. You have guaranteed Drell-Yan production. Now, of course, that's true for anything that's electroweak charged. If once you get to sort of high-ish energies, whether something is neutral but couples to the Z boson or charged, for production rates, it's not that big of a deal. But the difference is that something that is electroweak charged but electrically neutral could still be invisible, and then the phenomenology gets complicated. Something that's charged has to leave some visible signal in your detector. Now, if you want to cook up weirdo disappearing track things, that's fine. But basically, charged things have to be visible in some sense, okay? Whether it's the charged things themselves, if they're stable particles, or if they decay into charged things, charged standard model states. So it allows me to sort of say, if we can make it, we can see it, you know. And the main question is, and that's certainly true at lepton colliders, and the main question is, how much collider energy do I need to produce at least the lightest new charged state? Yeah. So if I have this space of solutions to g-2, how high energy a lepton collider do I need to build to guarantee that I can produce these things via just normal Drell-Yan production? Yeah. And in order to do this, we essentially perform this theory space maximization. Now, this is sort of an abstract equation of what we actually ended up doing, but it's sort of conceptually correct. So let me kind of walk through this, what I mean by this, okay? So I'm going to consider all electroweak scenarios for all possible masses and couplings that explain g-2. So, you know, metaphorically, in this little theory space, I'm going to look at each theory, whatever theory there is, with all the different parameter values and different parameters and different theories until I sort of cover, quote unquote, all of them. Okay, at least conceptually, that's where I am right now. So once I kind of scan over all possible theories, then within each theory, a single theory, I get, and this is a single theory with a single particle content and a single set of values for the parameters. Okay, I solve for the spectrum and I get the mass of the lightest BSM charged state. I don't care if there's another neutral one there. I don't care if there's heavier charged states there. The lightest BSM charged states. And I do that for all these theories. And then I ask for all these theories, what is the heaviest that this lowest lying new charged state could be? Yeah. So it's kind of a max min. Yeah. But this will tell me if the answer is 10 TeV, then across all the theories, there has to be at least one charged state at or below 10 TeV. Yeah. Subject to these constraints, and then you interpret them, Michael, as we do. Okay. So we'll get to that. Okay. But within these constraints, and you know, written in here is that we obey certain bounds on the couplings that we define in various ways. This is a precise statement. Okay. So within the electroweak simplified, so a model-exhaustive analysis, of course, is not a priori a new idea. It's kind of the thing you should be doing whenever you want to talk about direct signatures for some kind of low energy observable where you only get an EFT operator out of it, right? So for the RK anomaly, for whatever else, and that's kind of, you know, in some sense, whenever we model build, we kind of poke around in this space. But if you wanted to kind of get to the penultimate answer, you kind of should be doing this for every one of these low energy anomalies. Yeah. But of course, the problem is that doing some version, you know, for this particular kind of physics, we care about charged particle masses. So this is our irreducible physics direct signature that's associated with this low energy signature. And then we have to do this complicated theory space min-max. And if you had a different kind of anomaly, it would be a different kind of theory space min-max. But that's the part that's non-trivial. Now we're going to solve this by defining some simplified models which are engineered to produce the heaviest possible BSM charged masses while explaining g-2. And maximizing over the space of those simplified models will give us our answer, because all the theories that we did not include in the analysis will always give us lower charged particle masses. Now I should add at this point, I'm going to tell you about some very simple simplified models that we're using to perform this theory space maximization. But we actually explicitly checked many others that sort of step into broader and broader generality, and we confirmed through direct calculation that they all give us lighter masses. So I'm just going to focus on the two big guns. Okay, so the engineering specs for the simplified models is that we need a large chiral flip insertion, so that has to be a BSM coupling, we need a large Higgs web insertion. So that has to be a BSM coupling. That could be the same thing if it's a fermion, but it doesn't have to be. We need 3 new fields, a boson and a fermion and 2 of something. So either 2 of these or 2 of these. That's just angular momentum conservation. And then we posit that there's no new sources of electroweak symmetry breaking because we know how much electric symmetry breaking there is in total, and those will always have their own lower mass signatures. Yeah, because we're going to end up talking about TeV scales, and I think we can talk about this more. But essentially, once you start messing with that, 2x doublet models, etc., there's all kinds of new signatures that pop up. So we're going to make the pessimistic assumption that the electric symmetry breaking is done at model like. And in that case, we define 2 simplified models, SSF and FFS, 2 scalars and a fermion, 2 fermions and a scalar. And really, all you need to pay attention to is, here's a sort of typical diagram. Don't pay attention to where the photon attaches. The photon attaches wherever it does. This does not specify the gauge charges. Yeah, we are going to consider all possible, we're going to cycle through gauge charges for the new fields that are allowed. And the photon attaches wherever it does, okay? But the main point is you have, in the SSF model, you have 2 scalars and a fermion. You have a single fermion that talks to both left-handed and right-handed muon, and then you have a scalar that talks to left-handed muon, a different scalar talks to right-handed muon, and they mix via the Higgs. Or in this, you have 1 fermion that talks to left, 1 fermion that talks to right, and they mix via the Higgs, and a single scalar. These are complex scalars and vector-like fermions that acquire some mixing after electric symmetry breaking. We go through all possible representations, and we consider an arbitrary number of degrees of freedom, so degenerate copies of this. And like I've said, we've checked that other simplified models with different numbers of BSM fields, or Majorana fermions, or vectors, or real scalars, or pseudoscalars. They all give smaller g-2, and they all give lower masses for the new charged states. So this does not affect our theory space maximization.
Can you say roughly why that's true? I'm thinking specifically, I heard of some like leptoquark models where you just need one new guy, one new field, I thought, but I don't know any of the details.
No, sure.
Yeah.
No, I mean, you can get one new field and get a 2 TeV leptoquark, for sure, no problem. But I'm talking about these are going to be tens of TeV masses, Lance. So the point is, I mean, the reason why is, like I said, we've engineered these models to give you the largest possible masses. We're putting in big chirality flips, right?
Okay.
Like this thing is going to be, 4 pi or whatever it needs to be, right?
Whereas
so
those
if
things
you don't
that allow you to push up the masses more than in some model.
That's right.
Fields? Okay.
That's right. So every possible sort of model building, we've model built for perversity for these simplified models to push up the mass as much as possible. So this is by design. And then just to be sure, because we want it to be correct, we actually verified that if you add 2 and not 3 fields, if you have pseudoscales, all these other, we actually computed all of them to completion as well. But that's just not interesting because it just, as we would expect, it just gives you a lighter charge state. So we're going to be talking tens of TeV here. So this leptoquark thing might do 2 TeV, still plenty heavy, but not relevant from this side. Yeah. Good. So with this defined, it's now just purely algorithmic. We're just cranking the machine. Okay. So you go through quote unquote all possible electroweak representations. Now, when I say all possible, we cut off the process at representations that have electric charge of 2 or smaller, just because, things like, we found that as we calculated this, that the relevant answers didn't seem to hugely change as you went to higher and higher representations. And it's not like you could keep asymptoting. So we sort of, we were like, okay, so what is a reasonable way that you can motivate some range of possible representations in terms of reasonableness and also cosmology? Electric charges of bigger than 2 can be problematic, so let's just stop there. Let's stop at, we're going to have arbitrary number of degrees of freedom, but mentally we kind of have in mind 10ish or less. And we're going to have arbitrary SU2, but we're going to go singlets, doublets, and triplets. The reason we don't consider 4s and 5s, which you could with electric charge of 2 or less, is in some sense, we didn't find that the result depended on the rank of the SU2 representation all that much. And secondly, you're going to have crazy Landau poles if you have 4s and 5s floating around. So avoiding low-lying Landau poles is a way that you can justify both having, not crazy numbers of these things and not crazy charges or not crazy ranks. But again, this does not actually change the answer all that much, even if you were to go slightly higher. But okay, so you bound the space of electric representations a little bit. Oh shit, what just happened? Oh, that's weird. I want Calvin Hobbes again. There we go. Okay. So with all that said, I can just tell you the result, okay? Because at the end of the day, this was just turning a crank. So what is the result if I want to find this maximum possible charge mass? So let's start by imposing perturbative unitarity only. So we take all the couplings, all the, there's various cubic and Yukawa couplings and so on, and we just allow them all to be at the perturbative unitary limit. And as Michael has pointed out, at that point, your theory is, at that point, we treat the theory at that point as calculable as a sort of representative, edge case just to get to that highest mass. But really, at that point, the theory is not trustworthy anymore, and this is kind of like a strongly coupled theory. But it's kind of telling you that any remotely perturbative theory is significantly below this, and a strongly coupled theory is roughly here. Okay, that's how we should interpret this. And if we impose unitarity only, we get sort of 50 to 100 TeV masses. And that's roughly what you get parametrically. Like I said, this EFT analysis suggested 1/250 TeV, but if I put in sort of order 1 couplings or so, I can get sort of 20 TeV. Anyway, these are huge masses, and this theory space maximization can be performed by filling a table for the representations with the maximum charged particle mass that's possible in this compact parameter space. And this is not some random scan, it's just really a compact parameter space of manageable dimension, okay? And the answer is 100 TeV times square root of n BSM. So any perturbative theory lies way below this, and a strongly coupled theory lies roughly here, okay? Okay. So from unitarity alone, it seems that 100 TeV charge states could be the only signature. That's troubling, but let's put our model agnostic theorist hat back on. Now, when I say model agnostic, I mean, let me not care about the details of the model, about dark matter or supersymmetry or whatever. But let me just, take these things seriously. What would this mean for the nature of the universe, for physics and whatever? The first one is that if the g-2 was actually solved by these preposterous theories, this would make the hierarchy problem real, right? So, I mean, everyone here knows, but maybe for the younger folks, the hierarchy problem is usually explained in these seminars by, oh, you have the top quark and it's not canceled, and if you put a cutoff in there, it's top Yukawa times cutoff squared, and then the Russians in Minnesota will yell at you that it's all just regulator dependence and so on. But by the exact same token, really what this cutoff estimate is telling you is that the Higgs boson is quadratically sensitive to new physics. And this is made manifest in, if you have actual physics, like in the standard model, one could perhaps argue that if the UV is vaguely magical, then there is no hierarchy problem, technically speaking, okay? But once you say, I have the standard model plus fermions with a 4 pi Higgs coupling at 100 TeV, at that point, the standard model, there is a hierarchy problem, and it's completely real and it's completely finite, yeah? If you posit a 100 TeV state with a huge Higgs coupling, you have a finite Higgs correction, Higgs mass correction, that is of order the new physics mass, and it's huge compared to the physical Higgs mass. So this large, finite, and calculable Higgs mass correction is giving you a real hierarchy problem, and your theory is concretely tuned. Yeah, it's empirically tuned. You've measured something that exists and talks to the Higgs. So you have a problem if you believe in any notion of naturalness, no matter how generous. But there's actually more. There's 2 hierarchy problems. There's also a muarchy problem. The muon is now no longer technically natural because you've introduced some heavy new fermions that share the chiral symmetry of the muon. So the chiral protection that the muon enjoys to its mass now applies to sort of the muon / the F, which means that the muon Yukawa can receive corrections that are not proportional to itself, but proportional to all the BSM couplings. Yeah, and this will give you a calculable, finite, but again, large muon Yukawa correction. Yeah, an order 1 correction as opposed to order muon Yukawa correction. So the muon mass is no longer technically natural. So discovering these super high scale BSM solutions, so let's just say that you built a 400 TeV collider, and you found that g-2 is solved with 100 TeV charge states, and you measure and then these charge states have to have order 4 pi Higgs couplings, or square root of 4 pi Higgs couplings, you would prove that the universe is calculatively fine-tuned. So what would happen if the universe is not super fine-tuned? Yeah. So in some sense, whatever this upper bound has a dependence on the amount of tuning in the universe in some sense. Yeah. So let's just say that this tuning is not enormous, and we're going to impose a very conservative naturalness constraint. We're going to allow both the Higgs and the muon mass to be 1% tuned. Okay, it's a little arbitrary, but it's like, let's just say that both of them can be 1% tuned. Depending on how you define your tuning measure, that's 2 1% tunings. That's about 1 10 to the minus 4 tuning, but whatever. Okay, let's not split hairs. This looks to be a little bit tuned, but not crazily tuned. In that case, all the couplings are constrained to be much smaller than the unitarity limit. And now you do the exact same thing as before, and you get a different number. You get 20 TeV instead of 100, and you get a much weaker dependence on the number of new physics degrees of freedom, because with the number of new physics degrees of freedom, the tuning also goes up, so things kind of roughly cancel. Okay, so that's much more like it. That's still a very high scale, but much less crazy. Okay. So any notion of calculable, concrete, and conservative naturalness pushes the upper bound to the sort of 10 TeV scale. Okay, that's a little bit better. But there's another very model agnostic consequence we have to worry about, which is flavor physics. Yeah, the fact that we see g-2 in the muon means the muon's involved, means the leptons are involved, and things can get hairy. So if you have new couplings to the muon left and right, if you changed one of these couplings to talk to other leptons, you're going to have charged lepton flavor violating decay, mu to e gamma, basically. Okay, and there are very tight constraints on those, which means that in an anarchic model where there's no particular flavor structure, the lepton mass basis coupling of the electron to the muon has to be much smaller, and the other ones have to be constrained. So flavor anarchic models are highly disfavored. So there needs to be some kind of flavor structure. And the simplest ansatz for avoiding these flavor signals is minimal flavor violation, where you sort of posit that whatever physics solves the flavor puzzle, it comes from it generates the standard model Yukawas as spurions of some flavor symmetry that's being broken, and that's the only source of flavor breaking. And sort of anecdotally, if you look at more complicated non-MFE flavor models, you're going to get mass scales that are way lower than what we get. So this is sort of conservative. So if this is the simplest flavor solution, what that implies is that at least one of the BSM couplings in our theory has a tau counterpart that has to be higher, that is set by the tau Yukawa as opposed to the muon Yukawa. So if you want to preserve unitarity for all of those and not have non-perturbative physics mess up your flavor protection, then it's in fact the tau version that has to satisfy the unitarity bound. And now you are also pushed again to 20 TeV because your muonic version of the coupling has to be smaller by this factor of almost 20. Yeah. So flavor points us below the 20 TeV scale as well. Yeah. So flavor or naturalness separately impose a sort of roughly 20 TeV charged mass upper bound. Now, I would say both of these are pretty important. What if we impose them together? If we impose them together, we get 9 TeV, or call it 10 TeV, with fairly little dependence on the BSM multiplicity. Okay. Okay. So this is sort of our summary. Yeah. If you have only unitarity, you have sort of 100 TeV. Either flavor or naturalness, you have 20 TeV, and you have naturalness and flavor, you have sort of 10 TeV. So and these are super pushed to extreme bounds. Like I said, this theory at that mass scale is not really perturbative anymore. This theory is still 10 to the minus 4 tuned, and so on, right? So these are in that sense very conservative. So any reasonable theory wants to live way below 10 TeV. And conversely, not discovering charged states below 10 TeV would be proof of a tuned and flavor weird universe. Yeah, if g-2 is confirmed. Yeah. So putting all of this together, we can now assemble an experimental target for discovering BSM. By the way, how am I doing on time?
Yeah, feel free to take like 10, 15 minutes.
Okay, that's perfect. That's fine. Okay, so so you know what I'm going to do. So Lance and Michael, let me kind of go quickly through my spiel, and then maybe we can talk afterwards about the two-loop thing. Is that okay? just because.
Yeah,
Sorry, Lance and John and Michael. Yeah,
actually,
let me kind of go through things.
Sadly, I have to leave the meeting strictly in a few minutes to have another meeting. I'm really sorry, David. So maybe we can talk offline sometime. But anyway,
yeah, let's talk offline sometime. But I'll try and address this a little bit. Okay, I'll try and address it in passing. Okay.
Thank you.
So here's the sort of cartoon of the signature space, but it's not really a cartoon. It's actually a plot that you can bounce a quarter off of, right? Here is the BSM mass, and here is the quote unquote relevant coupling. And the meaning of the relevant coupling changes depending on what your general theory class is. If it's a singlet, then this is the coupling to the muon, and it goes proportional to the mass up until sort of roughly here. And if it's an Electroweak model, then it's the Electroweak coupling with some order 1 factor depending on the representation of the charge. But basically, it's plus minus a charge factor. It's here. And you don't care about the coupling to the muon because you can make it via the Strelian coupling. And this goes up to about 100 TeV and starts at a few hundred TeV from experimental constraints. And this is a very, very concrete experimental target. So how would we start covering it? The light stuff with very small couplings is going to be covered by low energy experiments and muon fixed target beams. Yeah. And by the way, John, this is essentially why I don't think the 2-loop thing is going to be a problem. The indirect signatures would just if the masses of the particles are that much lighter, then you would just be able to make them at these much lower experiments, and or the indirect signatures would show up rather than show up here, they would show up here. So it's because you have to have these indirect signatures, at the very least you'd get secondary confirmation. And it's just very hard to explicitly construct an example where this will escape, where even these 2-loop examples escape detection. But beyond that, let's have a longer conversation. / you can wait for a few weeks until we have an update.
Yeah, absolutely. That'd be great.
Yeah.
Thank you.
Yeah. Good. But okay, so you have low energy experiments that will cover this range. Within this range, there's strong motivation if the muon is the only coupling for a muon collider program, because you are colliding the particle that has the g-2 anomaly, and the coupling here is reasonable enough, and you actually can discover all of these very easily, as I'll explain. If you want to go to higher energies, you really need some high energy collider, and you need any lepton collider will do. Okay, so so if you can imagine building a 20 or 30 TeV electron collider, then that will be amazing. But just for sort of consistency of theme, I'm going to be focusing on order 10 TeV muon collider, because those are the kind of energies that are being discussed by the muon collider collaboration. So you could actually probe the space directly. Now up here, I don't have any if you start discussing 100 TeV muon colliders, you're being very optimistic indeed. Or 100 TeV any collider that's not proton, but of course for proton it's different because you cannot make 100 TeV or 50 TeV states at 100 TeV proton collider. But up here, like I've already said, the universe tastes strange and is provably tuned. So in some sense, if you've covered this whole parameter space and you've reached here with nothing discovered, then you know the theory is here and you've learned this about the universe. But even so, we'd like to confirm that this new physics exists, and indeed you can. At a, say, 30 TeV muon collider, you would still be able to, from this Daniel and Prida analysis, find the indirect signatures of g-2, even in these very high-scale Electroweak models. So I'll talk about that in a bit more detail in the last sort of 5 minutes. So on the low energy experiment side, a lot of singlet scenario parameter space is already excluded below a few GeV, right? So there's a lot of literature on this. Here's a bar plot for a sort of I guess this is a BL. This is a particular kind of gauge boson, a B minus L gauge boson, I think. And the g-2 favorite part's been excluded. However, a lot of that is still a little bit model specific and not completely exhaustive. Something that would be fully exhaustive before singlet masses below a few GeV would be a muon fixed target experiment, something like the M3 proposal at Fermilab or Na64mu at CERN, where you're essentially bouncing muons off a target, and if they make it, and you kind of make them emit singlet strahlung, and that singlet is either going to be missing energy or it's going to be something else, but you can essentially have complete coverage below a mass of several singlet GeV. Okay. So that is a model-independent way of probing singlets in the sort of near future. And this fully inclusive coverage below a GV is a very important near-term experimental opportunity, right? So being able to probe this in full generality to explain the G-2 solution is super attractive and super important. If you want to go above the sort of few GV scale, you're going to need high-energy machines. So muon colliders, I think everyone is sort of familiar that there's been a little bit of buzz about these as a possibility. There's been the sort of, the muon smashers guide came out. The muon collider working group at CERN has put out various documents, and there's significant progress in the muon cooling problem. I want to point you towards this particular Snowmass muon collider forum status update, where seemingly very serious accelerator people were saying like, oh yeah, the muon cooling we think is sort of at least a few TV muon collider we could totally do. Like you hear these words, and it's very exciting as a theorist to see this. This is a change from like 5 or 10 years ago in my understanding. So this is not a crazy idea, and they are awesome, right? Lepton colliders are wicked excellent. Yeah, you get all the energy from the beam to make new particles. You can do Higgs precision measurements. But of course, the thing that's really awesome about a muon collider is that it is perhaps plausible to go to tens of TeV of energy. Whereas for an electron collider, I don't know if that would be much more difficult. I'm choosing my words very carefully, Michael, but I think in some sense, this is what makes them very attractive. Yeah. So you can have high energy and lepton collider-like precision. So if muon colliders could be realized, they would be an incredibly attractive way of exploring high energy physics, both in terms of direct high energy signatures and precision and Higgs physics and so on. But the bonus is that they're also guaranteed to discover the new physics of G-2. In particular, let's talk about singlet scenarios. So if you have this singlet talking to the muon, you're going to have two kinds of unavoidable experimental signatures. You're going to have singlet production at the muon collider with photon initial state radiation. And in order to explore this, we did a fully inclusive muon collider physics analysis where we allow the singlet to decay into anything at once, including being invisible. So this is a super inclusive lepton collider analysis, which you can do because in a lepton collider, you know the center of mass frame. So you can tag this with a photon of a certain energy. You also have an indirect signature because the muon would have to talk to the singlet in such a way that you get deviations in elastic muon scattering, Baba scattering. And the muon collider is a bit special here because it's the only particle that collides it's the only machine that collides the particle that has the G-2 anomaly. So in some sense, you are guaranteed to see them in this scenario. So again, we considered muon colliders from a sort of hundreds of GeV scale to 3 TeV scale, and essentially all of them will discover all the singlet scenarios fairly easily. But in the case of a 3 TeV collider above a few GeV, you can just see it directly. That's the gamma plus X line with reasonable luminosities. For a 200 GeV collider, you can discover it directly even at a few GeV, and then you run out of energy. But at that point, Baba scattering corrections become huge. And this is the kind of thing where even a 2-loop scenario, you'd get these big Baba corrections. But anyway, longer discussion for another time. So a TeV scale or weak scale muon collider program would discover all the singlet solutions to the G-2 anomaly. And by the way, if the singlet was some strongly coupled silliness, then again, it's a little bit hard for me to imagine how this experimental story would change, right? Because you would just start either seeing the same Baba scattering deviations, or you would see high energy stuff being produced that's strongly coupled. So for experimental purposes, because even almost regardless of the muon collider energy, the combination of direct and indirect leads you to see this new signal. This is very robust with regards to strong coupling. Now for Electroweak scenarios, the phenomenology discussion is super simple. Basically, we say that if you can make it, you can see it. That has the usual understood caveats, but this is reasonably robust for a lepton collider. So you want to have a center of mass energy that's twice the mass. And again, so we have a 10 TeV mass here with some NBSM dependence. And this is a limit that's been pushed to sort of super ridiculous stretches. So, if I change this from 9 to 5 TeV, I would still say that that's the really, the reasonable within the, very close to the reasonable ceiling. So an order 10 TeV muon collider covers by far the most motivated parameter space. And you can say, let's build a 30 TeV collider if you want to be sure to catch all the remotely natural possibilities, okay? So a high energy order 10 TeV muon collider would discover all reasonable electroweak scenarios that account for the g-2 anomaly. But if you don't see anything, then the indirect H gamma signal that is induced by the same operator would show up. Yeah. So then, because if you do not see anything at 10 TeV or so, then the EFT is for the g-2 description is valid at high energies. You know, and then you know that there's a calculable mu to H gamma rate, and you can see this at a 30 TeV muon collider. But if you build a 30 TeV muon collider and you do not see these charge states, then you will see this mu to H gamma, and therefore you know that these charge states are there, but just at higher mass. So you've just proved that the universe is weird and tuned. Yeah, you've proved that there are these new states that couple to the Higgs that are that heavy. Yeah. So that brings me to the end, and the no-lose theorem can be summed up as follows. Okay. The first step is confirm the g-2 anomaly is real. The second step is you look for order GV or below scale singlet solutions at muon fixed target experiments. If you don't find that, then if you have a weak scale to TeV scale muon collider, you will discover all possible singlet solutions. And of course, you'll also start probing electroweak scenarios if you are at the TeV. If that doesn't find anything, building an order 10 TeV scale muon collider will discover all reasonable electroweak solutions and or observe the H gamma signal. So you either find new particles or you explicitly prove that the universe is explicitly calculably fine-tuned with weird flavor physics. So either way, you learn something really fundamental about the universe. And even though we like to discover new particles, I think it's not crazy to say that if you ended up in this scenario where you built a muon collider program and, you know, regardless of what else you find, maybe you even find supersymmetry, but if you don't find stuff that takes care of g-2, then there has to be stuff that's heavier and that couples the muon and the Higgs, and then that's insane. You know, then the way that we intuitively think about naturalness or what's reasonable in a theory is different. Maybe we have to start thinking about, you know, relaxions, vacuum selection, anthropics, all kinds of things, because that in some sense is even more fundamental than discovering a random particle that talks to the muon. That's it. Thank you very much.
Okay, well, yes, thank you very much for the talk. Let me just stop the recording.